Welcome to episode 2 of Biology for Bastards, teaching biology in the most profane way you've ever seen or heard. I'm your host, John Doty. Thanks for listening. If you've listened to chapter 1, great. We're actually going to get into some science this time, so things are going to get a little more complicated. So if you were confused by the first episode, you're going to be screwed. Because this one is all about the chemical context of life. And I know what you might be thinking. It's biology for bastards, not chemistry for bastards. So what the hell's going on? They go hand in hand. Biology is just a bunch of shit floating around and juices, and those juices and shit interacting. And that's basically life. That's what we got to talk about. As always, a PowerPoint will be linked to in the show notes so you could follow along. And let's get going. Alright, so this chemistry stuff. First up, what we've got to do is distinguish between matter and energy. Okay, so we've already talked about how life needs energy, but it's a little bit different in chemistry, and then matter is just shit. Matter's shit. It's just stuff that takes up space. Has mass, takes up space, that's matter. Could be air, could be a liquid, could be a solid, whatever it is, that's matter. Pretty much everything we talk about in life is matter, so we don't have to deal with not matter in biology, which makes our life easy. But energy, we've got all these different types of energy. We've got potential, we've got kinetic, we've got sound, we've got light, we've got heat, we've got the stuff that you eat, all that fun stuff. That's all energy. Now, when we start going into detail about the different types of matter, we have atoms, which hopefully you know, protons, neutrons, electrons. Protons and neutrons in the middle, electrons on the outside. And then we have elements. So an element is as pure as it can get. Can't be broken down into anything else. Periodic table, if you're an idiot. Those 118 things. That is all the elements, or those are all the elements that we have. Okay, hydrogen, nitrogen, oxygen, all this stuff. And if you start combining those, then you get a compound. A compound is two or more elements, so it's not just like two oxygens stuck together. It's two or more elements in a fixed ratio. So water, hopefully you know, is H2O, 2 hydrogens, 1 oxygen. Every single fucking time, that is water. H2O2 is not water. That is hydrogen peroxide. You drink that, bad things happen. H2O, that is good. You drink that, good things happen. HO, that's a hoe. We'll just leave it at that. Actually, hoes are good. If you go O's, OH, because that's alcohols. So that's fun. As long as it's not one of the alcohols that like make you blind and make your kidneys shut down. But if it's the right alcohol, that's good stuff. Now, when it comes to life, there's a whole bunch of elements that are important, about 25 of them. But really, only, 5, 6 are super, super important. The other ones, whatever. Who gives a shit about them? Things like boron, chromium, copper, iodine, tin, zinc, all that. Who gives a fuck? What you do care about are your carbon, hydrogen, oxygen, nitrogen. Those are the big 4. And then sulfur and phosphorus. Potassium can hang out too. But really, I just remember SPONCH. SPONCH. Sulfur, phosphorus, oxygen, nitrogen, carbon, hydrogen. SPONCH. That makes up life. And those are the super, super, super important ones you can't do without. Now, I mentioned atoms already. Okay, protons, neutrons, electrons. That is as small as you can get and still be matter. Okay, everything in the fucking universe is nothing but protons, neutrons, and electrons arranged in some weird way that makes it into a person, into a table, into the air you breathe, all that stuff. Right? So, when you talk about atoms, you can have mass, you can have charges, you get atomic numbers, all that stuff. We're not going to go into too much detail because that's really straightforward. Mass is just your protons and neutrons. That's it. You add the two things together, that's your mass. The electrons don't count because they're too freaking tiny. Your atomic number, that is your number of protons. That's all it is. That's the number on the periodic table where it goes hydrogen 1, helium 2, blah, 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 oxygen 8, carbon 6. That atomic number tells you how many protons. The symbols, whatever. Some are Latin, some have other meanings, some make a lot of sense. Whatever. This is biology, not fucking chemistry, so who gives a shit? If you want to know how I really feel about chemistry. Now, we do have these things called isotopes that pop up. And a lot of times you hear about them, and they're radioactive isotopes because they're used a lot in medicine. Or if there's like a nuclear disaster, you got to worry about the radioactive isotopes because you don't want to get cancer and die, which is bad. But I do recommend, off topic here, this is not an ad, but it is an ad. It's unpaid. I just really enjoyed it. The show Chernobyl on HBO, 4-part miniseries. Very, very, very good. Learn all about radioactive isotopes on that thing. Now, in order to be an isotope, you have to be the same type of atom. So you have the same atomic number, which means the same number of protons. But what makes you different is the number of neutrons. So your nucleus is bigger or smaller. Your mass is bigger or smaller. And there's a magic ratio where atoms like to have for protons and neutrons. And when you get too far away from that, that ratio is off. And they basically become unhappy with their body image and they want to change. And they change by throwing parts of themselves away. That's what radioactivity is. Just what exactly they're throwing out. So that's one type of energy. But what we're really going to talk about with some energy kind of coming on here is the capacity to cause change, because we really care about potential energy stored in chemical bonds. Now, you can have potential energy from a bunch of stuff. Climbing up a ladder gives you potential energy because you can just fall off the ladder easier than falling off the ground. Okay, so potential energy, as far as biology is concerned, is because of its structure. The energy stored in chemical bonds. Now, these bonds form when the valence electrons, so electrons on the very outside, when those electrons start to interact with each other. You can think of the atom as an M&M, and the candy shell is the very outside layer. That's what's going to interact with stuff. So you start getting different types of bonds forming when you start interacting different valence electrons, depending on some stuff that we're not going to get into. You can hear about, electron orbitals. Those are shit. I don't care about that. Take chemistry. But what is important is the very outside, the valence shell, has to have 8 electrons. That's its happy little number. It's totally full when it has 8. So that's what's going to determine whether or not bonds form, is whether or not they have those 8 valence electrons, whether they need to gain some electrons to get to 8, whether they can lose some electrons and get down to 8. It's kind of like a jawbreaker where it's layered. But that is what determines the bonds an atom can form, is what does it need to do to get to those 8 valence electrons. Now, when it comes to different bond types, there's a couple. There's ionic bonds, there's covalent bonds, there's metallic bonds, which we don't give a shit about because we're not robots, so we don't have metallic bonds in our body. So we really focus on two real types of bonds, covalent and ionic, and then two half bonds, we'll call them. They're like honorary bonds. They're just so fucking awesome that we call them bonds even though they're not bonds. And depending on who you talk to, if you argue with a chemist, they're going to talk about ionic bonds being a stronger bond, having more bond energy than a covalent bond. But life is nothing but solution. We're dissolved, we're shit dissolved in juices and all that stuff. Ionic bonds, when you put them in a solution, they break up. They disassociate. Covalent bonds don't. So in biology, most of the super strong bonds are actually going to be covalent bonds. So it's different from chemistry. But we don't give a shit about chemistry because biology is better. That's why it starts with a B. Chemistry, I can't think of a insulting word that starts with a C. Not cool. Whatever. Bonds. Covalent bonds. You share electrons. So you're trying to get those 8, but you're going to share them. So that's what we get with water. You have hydrogen sharing an electron with oxygen. You have the other hydrogen sharing another electron with the oxygen. That gives hydrogen their happy number, which they're special, they only want 2. And it gives oxygen their happy number. So everybody's happy. Everybody's good. Sometimes that sharing's not equal. So think of, covalent bonds as custody. Actually, just think of any chemical bonds as child custody. In covalent, you have joint custody. And sometimes you can have a nonpolar bond where things are shared equally. So both atoms have an equal share of the electrons. It can be found around one atom just as often as it's found around the other. Or you can have polar bonds. And this is what happens when it's unequal custody. Okay, it has to do with electronegativity, which just means an atom really freaking loves electrons and just like pulls the shit out of them and brings them over and holds them close and is very rude and stingy with them. Oxygen is very electronegative. But with this, one atom has more custody than the other. So it's more closely found to oxygen than it is to the hydrogen if we're talking about water. And when you do this, weird interactions can happen, and that's what we're going to get to after we talk about ionic bonds in just a second. But one last thing about covalent, so you can have single covalent where you're sharing 2 electrons. You can have double covalent where you're sharing 4 electrons. You can have very strong bonds and be a triple bond where you're sharing 6 electrons. That's what happens with nitrogen in the atmosphere, which is what makes nitrogen very unreactive. Here's a little side note, might blow the fuck out of your brains. Bags of chips, when you buy them, full of air, right? Wrong. Okay, it's full of nitrogen. Because if it was full of air, they'd be stale as soon as you open it. It's full of nitrogen, which is unreactive, so it keeps everything fresh. And that's why there's so much gas in the bag to surround all the chips and keep them from interacting. So there you go. So don't bitch about the amount of gas or the small amount of chips in the bag, because they're doing that to keep them fresh for you. So shut the fuck up. Alright, ionic bonds. Moving on. In custody, this is where one atom has full custody, the other one gave up parental rights. One atom gains electrons, the other completely loses it. And then they become positive and negative, depending on if they lose or gain electrons. If they lose the electron, they become positive. We call that a cation. And then if they gain electrons, they become negative. We call that anion. A-N-I-O-N for anion, cation, C-A-T-I-O-N. Okay? And like I said, these are typically very strong unless you put them in solution, and they do dissociate. So that's why we list them as weaker than the covalent bonds as far as biology is concerned. Now, the last 2 things we're going to talk about are just special types of interactions. They're not actually bonds. They're just preferences. And it has to do with that polar covalent bonds we talked about, that unequal joint custody, where one atom pulls on the electrons harder than the other, so it has a slight negative charge to it, while the other side that doesn't pull nearly as hard has a slight positive. So with water, it's always our go-to example because we're just water. Okay, oxygen is slightly negative, hydrogen slightly positive. Now this can cause hydrogen bonds to form, which again, they're not actually bonds. We're not doing anything with the electrons, except we have areas that are slightly negative, kind of arranging and facing areas of slightly positive, or vice versa. Okay, so it's a preference. It would much rather look at the opposite sign than at the same sign. Pretty much what it does. So you can think of hydrogen bonds as Velcro. They will come up a shit ton as we go through. It's what, holds proteins together, to certain structures of protein. It holds your DNA together. Individually, they are very weak, but when you get a whole bunch of them thrown together, they're actually quite strong. And then a little bit weaker than those, but same general idea, these things called van der Waals interactions, or van der Waals forces. They're super weak. They're like the really shitty Velcro you get at the dollar store. It's not like the good Velcro brand Velcro, where you get these slight interactions happening as things move around. But it does, have some sort of power. It's how geckos stick to shit. They don't have sticky toes. They actually have hairs upon hairs upon hairs upon hairs on their toes that they interact molecularly to whatever they stick to. And that allows them to actually stick. Now, the three big ones that we talked about, the covalent, the ionic, and the hydrogen bonds, they're all important for life. All of them. Okay, covalent are really good to make lasting stuff. So we're going to talk about what type of things are formed, these things called macromolecules, a little bit later, in a later episode. And those are all formed from covalent bonds. And it's because they are very, very strong. So you can kind of think of those as almost the permanent or the semi-permanent bonds happening in life. And then we have our ionic bonds that are really good for quick reactions, quick responses. Calcium, potassium, all those electrolytes that you've heard of, the sodium, those are really, really good. We get them from ionic bonds. They're used to do all these quick little responses in your body to keep you alive and not die. And then hydrogen bonds, the weakest ones that we care about, they are good kind of temporary holds. When we've got to take stuff apart and put stuff together a bunch, that's where hydrogen bonds become super, super important. Now, when you have these different bonds, that is going to determine the shape of whatever molecule you have. Again, this is, we skipped the orbital stuff. We skipped a bunch of chemistry because it's too dry and boring. But the shape is super important because, as we will learn, shape determines function. You fuck with the shape, you fuck with the function. It's just simple as that. And if you have similar shapes, you can have similar functions, or you can mimic other things. That's how morphine and heroin kind of are related. Heroin mimics the stuff that gives you pain relief. And that's why apparently heroin feels really good. I don't suggest doing it. But it's a free world. Just, don't die. Also, don't do drugs. Drugs are bad, but I can't stop you from doing anything because you're a bastard, which is why you're listening. Okay. And then last but not least for today is how these bonds form. And they form through chemical reactions, where we have things going in, those are called reactants. We have things coming out of them, those are the products. Sometimes we have reactions that are reversible, where it can go in or come out, and it's the same thing, forward or backwards, either one works. And when we do have these reversible reactions, we will have things called chemical equilibrium or dynamic equilibrium. this is where our reactions in both directions kind of cancel each other out. We have just as much happening in one direction as is happening in the other direction, and everything remains equal. So we're still making stuff in both directions. We're just making stuff at the same rate. So we are making food at the same rate that we're eating it. So you never gain, you never lose. Everything just kind of maintains the same. And with that, that's chapter 2. Chemistry. Done and done. So a little closing here. This has been Biology for Bastards, and I'm your host, John Doty. Really appreciate you listening. Please rate, subscribe, tell everybody you know about it. Spread the word. Let's get this thing going so I can quit my job and just do this forever. Our intro and outro music is Feeling Good by Purple Planet Music. It's a free song, so yay them. I just have to mention their name, which I did, so now I'm not illegal, and all is good. So with that, thanks again for listening, and we'll hear from you next time.